All right. Hey, everyone. This is the last hour, or the third hour of Physics 1A for March 22nd. And we're looking at this setup right here. There's a kind of a tabletop with pulleys on both ends with a rope that connects three different objects here. And our goal is to find the acceleration of the system shown and the tension in each chord. And there's friction on this upper surface right here. The pulleys, we're going to say, are perfect, which basically means that they don't have any inertia. So they're massless, and they are also frictionless. All right, so they rotate without friction. In addition, the cable that connects all of these things, we're going to say that it remains tight the entire time, and it's not elastic. So the distance between, for example, the 10 kilogram and the 5 kilogram is always going to be the same distance. Real cables tend to stretch. These are not like that. They're perfect cables and perfect pulleys. And our goal is to find the acceleration of the system. All right, so the first thing to do is to try to figure out, just based on the numbers given in the problem, what direction do you all think that this system is going to accelerate? Yeah, to the right, right? Okay. So we're pretty sure that because this is 10 kilograms and this is 5 kilograms and this one is on a flat surface, that it's probably the case that this object is going to accelerate down this way. This object is going to accelerate to the right. And this one is going to accelerate up. And I think I'm zoomed out a little too far here. I'll zoom in just a little bit. I wonder if I select all of this, will it let me just scale everything? Yeah, it will. Okay, there we go. All right, so that's our setup. We know the acceleration moves in this direction, and that's going to inform how we draw our free body diagrams. So let us draw free body diagrams. Let's start with the one that's over here on the left. Maybe I can go left to right down here, and then we can do the calculations over here on the right. Let's see if we can do that. So the 5 kilogram object, it's going to have two forces. There's going to be a tension force pulling up this way that I'm going to call T sub 1. So we're going to say there's an upward force on this one. Okay, I have to do all this one. All right, the one on the left, the 5 kilogram object, we're going to have a tension force pointing up this way. There's also going to be a weight that's pointing downwards. Like this. And of these two, which one should be larger, the tension or the weight? The tension, yeah, exactly. So this one we need to make bigger because it's going up, right? So this is going to be, oh my god. This one that goes up is T1. The one that goes down, we're just going to say is mass times gravity. So I'm going to call this M1. So we're basically going to go M1 right here. This is going to be M2, and this is going to be M3. Now these have the same value, but we'll just say up here that, M1 is 5 kg, M2 is equal to M3 is equal to 10 kg. And then we can just use the weight to identify what it is. And then in addition to that, this whole system is accelerating upwards. Since they're all connected together, they're going to have the same accelerations. All right, so that's the first one. Let's do M3 next, because the other one's going to need a little bit more room. For M3, we're going to have this one over here. For M3, we're going to have a weight pointing downwards, like that. And we're going to have a tension pointing upwards. And I'm going to call the tension in this cable over here to be T sub 2. And I'm going to make the weight bigger in this case. So the upward force here is going to be T sub 2. And the downward force is going to be M3 times G. And the acceleration in this system is going to go downwards. That means that we're going to make, for the first one, we're going to make up positive y. And for this one, we're going to make down positive y. Because we always want to make the direction of the acceleration positive. All right, finally, we're going to have M2. We'll draw that one up here. So we'll have, so put a little dot. Let's put it right here, I guess. No, we'll go over to the right because we want to leave room for the math for the other ones. So for M3, which is on this surface right here, it's going to have a force of tension that goes this way. it's going to have a force of tension that goes back the other way. Those are going to be our T2 and T1. It moves to the right, so I'm going to make T2 bigger than T1 on my picture. We also have a normal force, which is going to be pointing straight up. And finally, we're going to have a weight that points down. God, that looks awful. In. There we go. And then we're going to have a weight that points straight down. And this weight, unlike most of the problems we've done, is actually going to be equal to the normal force. And this will be m2g. This system accelerates to the right this way, so I'm going to make that direction the positive x direction. And we'll make up positive y. And now we merely need to connect all of these together. There might be enough room that I could just move this one over just a little bit, I think. All right, so let's go left to right, and let's write down all of our equations. So for this one that's over here on the left, we're going to have net force acting in the y direction should be equal to the mass. In this case, the mass is m1. So we're going to write m1 times the acceleration. There's two forces. There's T1 and m1g. So m1g is down, so we'll make that one negative. So T1 minus m1 times g is equal to m1 times a. Oh yeah, you're right. There's another force. Here, let's draw that with another color. So there's going to be a force back this way as well, which is going to be the friction force. So that is the friction force. We'll just call it F sub k because it's sliding. And now I should technically... I should really make this longer now. This one needs to be bigger than the sum of the other two over here. And it feels like that's kind of at an angle. We don't want it to be at an angle. There we go. That looks like straight. Okay, so that's our equation for the first one. This equation has two unknowns, which are T1 and A, so we really can't solve this equation for anything. Next, we want to do the other hanging object over here. And once again, we'll just say net force acting in the y direction on this object should be equal to its mass. This mass is m3 times A. On the left-hand side, we'll have m3g minus T2. And that's all we can do with that, because once again, we have two unknowns, T2 and A. And between the two equations, we now have three unknowns, because T1 is the third unknown. So these two equations, we don't have enough information. We have to use this other one up here. For that one, move it back to the left. We're going to have net force in the x direction equal to the mass, which is m2, times the acceleration in the x direction, which is a. And then net force in the y direction, which is going to be equal to 0, because there is no y acceleration. This one's going to be really easy to do. There's a normal force up and m2g down. That means that n minus m2g has to be equal to 0. So that means that n is equal to m2g. In the x direction, we have three forces. We have T2, T1, and the friction force. So we'll write T2 minus T1 minus the friction force should be equal to m2 times a. Now, those are all the equations. Before I start doing other things, does this setup make sense as to why I did all this stuff? And does anyone have any questions?
Why'd you put EFX equals M2A? Why not just M?
Well, because there's three different masses here. So I wanted to be clear that for the first picture, it was M1A. For this second picture, it's M3A. And for this one, it's M2A.
Oh, my bad. I'm just reading it wrong.
There's three different ones. That's okay. All right. So the next thing we want to do is to kind of solve for the three variables we have. We also can use, of course, the equation that the friction force is equal to the coefficient of kinetic friction times the normal force. So if you plug that in here, we're going to have T2 minus T1 minus mu k times n. But look, n is equal to mg. So really the friction force is going to be mu k times m2g. So we have replacing the friction force with m2g times mu k. And all of that should be equal to m2a. Trying to keep all this stuff separate. Maybe I should just make this a different color so it doesn't really... just make it purple or something. Alrighty, so what we have now are three equations. We have this one, and the other one. And we need to solve them. Now, in my opinion, there is a really, really easy way to do this. You can solve this like any way that you want. It does not matter how you solve it. Probably the normal method would be the substitution method, where you solve for t1 in this equation, and then you solve for t2 in this equation, and then plug them in for t1 and t2 right here, and then you solve for the accelerate. That's the normal way to do it, probably, right? But there's kind of an easier way to do it. What's another way that we could do this? We can add the first and second equations. And this one, right? We can add them all together, right? That's what you want to do, Chris? We can basically say that if I take this equation, call it equation 1, I call this equation equation 2, and I call this equation 3, that I can basically just add the three equations together, right? So let's do that. So we take equation 1 plus equation 2 plus equation 3. We're going to stack at them, okay? And I'll just copy paste them to just make this kind of quicker. So we'll take this piece, we'll copy it, and then we'll paste it right here. Didn't leave much room for myself, did I? Let's scoot this down just a little bit. All right, so that's equation 1, and then we have equation 2. Copy paste that, put that one right underneath it. Trying to kind of line up these equal signs, and then we take equation 3. All right, so we line up all these equal signs, and then now I'll actually. So this was 2. Whoops. There we go. That's equation 2. That's our. No, don't do that. Stop it. That's equation 1, and we're going to add to that equation 3. There we go. We're adding all of these together like this. So we stack add, and what we get on the right-hand side, we have M1A, M3A, M2A. I'm just going to shorten that by saying everything is times A, so we can just say M1 plus M2 plus M3, all multiplied by the acceleration. Total mass times acceleration. And then when I add the rest of these together, what you notice is that T1 is positive here, but it's negative here, so when we add those will cancel. And T2 is positive here, but it's negative there, so when we add those, it will cancel. And what we're left with is only one thing is positive, which is M3G, so I'll put that one first, minus M1G, and then minus the friction force. And there's our equation. Now we want to solve for A, but I want to just kind of look at this equation for a second and make sure that you all understand that you can kind of think about this and make sure it makes some kind of a sense, right? I think I need the picture here too. So when we look at this picture right here, you think about what is it that actually makes it move down. The reason why you all knew that it was going to move down was because this was the heaviest object, right? Of the two hanging objects. So you knew it was going to go down. So really, the downward force is entirely coming from this, right? It's the M3G. That's the weight of this object is where the downward force is coming from, right? So that shows up here as a positive. And that should hopefully make sense. It's saying the weight of that object, right? Minus the weight of this object, because this object is slowing it down, right? So the weight of the third object minus the weight of the first object. And then the other thing that's slowing the object down from moving is the friction force, right? So these two things combine together to slow the falling of M3G. So pretty much if you think about it, what the left-hand side, what the left-hand side of this equation says is the net force acting on the system is equal to the total mass of the system multiplied by the acceleration. And you know, sometimes when you're doing your homework, you can use that to kind of look at your work and see, like, does this actually make sense? You know? All right, so now we just want to solve for the acceleration. But before we do that, does anyone have any questions? Okay. Now there's a g in all these terms, so I'm going to basically factor that out when I do this. So I'm going to say M3 was 10, M1 was 5, UK was 0.2, M2 is 10 also. All of the, all of that is multiplied by g, so times 9.8. And then we divide all of this by m1 plus m2 plus m3, which is going to be 25, but I'll write it out. So m1 was 5. That was this guy. m2 is 10. And m3 was also 10. I think you can do this in your head, because it's 10 minus 5, which is 5, minus 1 over 5 times 10, which is 2. So this is 5 minus 2, which is 3, divided by 25. Yeah, you can't really do it in your head, can you? 3 over 25 is... I don't know. You all tell me. What is the answer? You basically get 3g over 25, which you're telling me is approximately equal to we'll call it 1.2 meters per second squared. That looks like the right number to me. The number you put there looks like the right number to me. Do you all agree that you get about 1.2? Okay, great. All right, so it's not really that hard of a problem. It's just I just want to show you how I do these type of problems. You can do however you want to, as long as it works out for you. But this is my method. Make the acceleration positive, draw free body diagrams, solve all these things. You can. The way I see it, if you don't know how to solve a problem, this is what you want to do. If you don't initially know what you need to do, just follow this kind of algorithm. The algorithm is, number 1, draw a free body diagram. Number 2, make XY axes. Number 3, make components of any forces that don't point along the axes. And then when you define the axes, make sure you make the positive direction the same as the acceleration. And then use Newton's laws. And then just it should all work out. If the problem isn't, if the problem is solvable, that should all work out. All right. So, any questions at all about that problem before we move on? Okay, if not, let us try this one. So in this problem, what we have is there's a cart on the bottom, or a wedge. We call this one the wedge, I guess, on the bottom. And the wedge is being pushed by a force F. The whole system is accelerating to the right. And our goal is to find the size of the force F such that the small cart, little m, does not move relative to the wedge, big M. Okay? So the whole system is accelerating because of this force that's pushing this way, and the goal is to make it so that this little cart does not fall off. Now, to understand what's going on, if the force was 0, what would this little cart on top do? If we don't push it with any force at all, we just leave it be, what's the system going to do?
It's going to fall?
It's going to slide down. What's the wedge going to do? Is the wedge going to stay still? It'll go the other way, right? Yeah, exactly. So if the little cart goes to the right, the wedge is going to have to move to the left. Okay. So we know that if we want to actually prevent that from happening, we need to push in the right direction. If we push to the right, then it's conceivable that if we push hard enough, that as that cart tries to fall down, if there's a big enough force supporting it from the wedge right here, it's conceivable that it will stay up, basically, right? And that's basically what we want to do here. All right. So once again, trying to solve this through some type of shortcut or thinking about... There's probably ways to solve this where you avoid all the things we're about to do. But I am quite simply not smart enough to do those kind of things. I'm a very... I don't like to skip steps, I guess. Because when I do, then I sometimes don't understand why I skipped it. Even if somebody teaches me like a shortcut method for something, I always want to just like put all the extra steps in because it's just too hard to solve some of this stuff. There's just too many things going on. There's too many little forces here and there. So the best way is to just keep it simple and use the same method that we've used up till now, right? And that method means that there's two objects. So we're going to draw two free body diagrams. We're going to create, coordinate systems, and we're just going to go from there. Kelvin says, you also find it easier to find mistakes when you write every step out. Yeah, I totally agree with you. It's when you skip steps that you start kind of losing minus signs and losing factors of 2 and stuff like that, right? Okay, so, all right. So let's draw diagrams for each of these. So we'll do, I guess the wedge is, no, let's do the cart first. Okay, so for the cart, that's on the wedge. We want to draw a free body diagram. Now, because the cart is sitting on an inclined plane here, I'm going to start off by drawing a little line to represent that plane. So this is going to be the surface of the wedge, basically, on which our cart sits. And we'll go ahead and just draw our forces on our cart. So this is going to be a little dot to represent our cart, and I'll just have you tell me, what are the forces that are acting on this cart? There's a weight, and there's a normal force. Yep. So our weight is going to go straight down like this. Call that one. Since it's little m, we'll call this one mg. There is no friction in this problem. So the wheels effectively here are going to make it so that there isn't any friction. All right. Realistically, what that means is there is enough friction so that the wheels don't like slide in place like tires in the mud. But it means that there's not going to be any meaningful friction. Yeah, exactly. So that's the weight. Actually, I probably should actually make this a different color since I'm making the surface black. So let's make this blue or something. Oh no. We're getting to that point when I might need to start a new OneNote page because this is getting out of control slow. All right, that should be the normal force. And once again, I'm going to measure that I made this one long enough. I didn't. I'm going to make it shorter. So let's make it a little shorter. And again, I want to make this equal to the y component of my normal force. All right, there we go. It's pretty close. So that's mg and that's n. Can you all think of any other forces? People mention friction, but yeah, we're saying there's no friction here, so that's it, right? Those are the only 2 forces that are acting on this object. All right, so we could actually just go ahead and start solving this part of the problem if we want to. We might as well. So let me move the mg over here, and then I'm going to draw one more line in here to just go through and show you how we get the angles right. We've done this before, but it doesn't hurt to do it again. I'm sure we can do this a million times and people would still benefit from seeing it. So I'm going to make axes. Now, how do I want to make these axes? How do I want to set up my axes? The acceleration of the system is to the right, right? You want positive x to the right, exactly. So this needs to be one of our axes right here, right? So what we're going to do then is we're just going to draw in some coordinate axes. So we're going to have, this is going to be the positive x direction right here. And then the positive y direction is going to point perpendicular to that. So it's going to be straight up and down. There's our positive y direction. And now I can see that this is slightly not straight and it's bothering me, so we'll try to make it more straight. There we go. All right, so this is going to be the positive x direction. This is going to be the positive y direction. I didn't really mean for this to be right on the axis. I'm going to shift off just a little bit. The acceleration is in this direction, though. And yeah, we've got our x and y coordinates. So now we basically need to break up the normal force right here. But the question becomes, what actually is the right angle to make the angle theta? Is it going to be this angle or is it going to be this angle? It has to be one of them. So I'm going to tell you to use your intuition and look at the triangle down here and think about the upper angle and the bottom angle. Which angle of those two is smaller? This one or the angle theta? Which one is smaller? The upper angle or the angle down here? The bottom one, right? Yeah. This one is definitely smaller, right? Okay. So, if you were to guess between this angle right here and this angle right here, let's call them 1 and 2, which of those two do you think is theta? Number 1. There's no doubt about it that 1 is smaller than 2, right? And that's true. It absolutely is. So that, in my opinion, is always like the simplest thing to do is just be like, it's probably this one. And then you can go about proving it. And the way you would prove it is to say, since this is theta and this is the ground, the x-axis is parallel to that, which means that this is also theta, which means that because the normal force makes a right angle with the surface, this has to be 90 minus theta, which then means that that angle, by default, has to be theta, because the sum of this one plus this one has to be 90. All right. So, however you prove that for yourself, there's multiple ways to prove it. Is fine, but I think it's a good idea to just draw to scale and kind of just like notice that these two angles look to be about the same. All right. So then we want to use our two equations. So we're going to have net force acting in the x direction is equal to the mass of our object, which is little m, times its acceleration. And the net force in the y direction should be equal to may. What is the acceleration in the y direction going to be for this object? Keep in mind that it says, find the force F such that the small cart does not move relative to the wedge. If it doesn't move relative to the wedge, that means it doesn't go up, it doesn't go down. It stays right at the same elevation, and that means if its y-coordinate is going to be constant, that the acceleration in the y direction is 0. Exactly. Oh, I left out a step. We need to break up these forces into components. So this force N is going to have a component that's going to point this way, and it's going to have a component that'll point up this way. Remember that when you're drawing your components here, you need to make sure that they actually add together to give you the vector you're looking at. That is to say, we need to go up and to the right to have a vector that goes up and to the right. You don't want to make one of these vectors pointing the other way, which is what some people sometimes will do. So n is the hypotenuse, which means this side over here is going to be n times the cosine of theta, and the sign on the top will be n times the sine of theta. There we go. In the x direction, then, this will be the only force that we have. So we'll have n times the sine of theta is equal to ma. In the y direction, we have n cos theta pointing up, minus mg, which is going down. And all of that's equal to 0. Between these two equations... Oh. Oh, we're not solving for A, we're solving for F. I was like, we can just solve for A. We might as well go ahead and solve for the acceleration because we can, though, right? So this n is going to be equal to mg over cos theta. Plug that in for n right here, so we'll have mg over cos theta times sine theta is equal to ma, which means that the acceleration, okay, this is not being blocked, right? The acceleration is going to be equal to sine over cosine times g, so g times the tan of theta, and the masses cancel out. So that will be handy for us in the next part of the problem. Gotta stop looking at my second monitor and trying to draw. That does not work. So acceleration is g tan theta, and we got all that information just from the cart. All right. The next thing we want to do is our wedge on the bottom over here. So for the wedge, we want to label all the forces acting on the wedge. Once again, it is probably going to be useful to go ahead and grab this line over here that we drew to represent the plane. We're going to need to have that on our picture right here as well. So what are the forces that are acting on the wedge? What are those going to be? There's the force F, that's right, which points to the right. There's its weight, and there's the normal force. All right, let's start drawing those forces. So we're going to have the force F is going to go this way. That's F. We have, wouldn't the normal force equal the y component of I'm going to come back to that question. Are you talking about, Joanne, you mean on the picture for the cart? Or do you mean on the picture for the wedge that we're about to draw? For the cart? Wouldn't the normal force equal the y component of mg, not the other way around? Did I mess that up? Oh, I see what you're saying. I see what you're saying. Shouldn't the normal force be smaller than gravity? First of all, depending on what coordinate system you choose, what you said could be true, right? Like, if we'd chosen a coordinate system such that this direction was the x direction, then what you said would be true. But this cart isn't actually sliding down the wedge. And so, as a result, the normal force actually has to be greater than the weight in order to support the cart from falling down the ramp, I believe. If the cart was going down the ramp, then what you said would be true, that the normal force would be the y component of mg, right? But this system is accelerating to the right instead of accelerating down. That's a really good question. No one's really ever asked that before. That's a really good point, though, that this is kind of counterintuitive, because if you look at what the normal force says right here, it says the normal force is equal to mg over cos theta. And in case you don't know, cos theta is always a number between 0 and 1, which means in this case that the normal force has to be greater than the weight. And that's I think what you're pointing out, right, Joanne? Is that this is kind of weird, that the normal force is greater than the weight in this case. And so what I'm going to say is that it needs to be greater than the weight, because otherwise the weight would overcome the n cosine theta and the object would slide down the ramp. Right? So you need to have something that's holding, you basically need something that's holding the cart up, and there's really only one thing to hold the cart up, which is the normal force, basically. So that's what's going on here. Yeah. It's a really good question, actually. No one's ever asked that before. That's a really, really good point. Okay. So, all right. So the force, okay, back on the wedge. We've got the force F, which points to the right. And we've got, as you all mentioned, there's going to be a normal force coming up from the ground. So we're going to have a normal force going up this way. I'm going to label that one to be n sub g. Well, actually, I'm going to call it n ground, just so it's clear that this is the normal force coming from the ground, acting basically here and here. These two are going to combine together to just be one force, basically, which I'm going to call the normal force from the ground. We also have the weight, which is going straight down. This is going to be defined as capital Mg. And let me go back up. Any other forces acting on the wedge?
Would like Newton's third law make the normal go the opposite from the mini car?
That's exactly right. That's exactly right. So we need to have this force right here. This force is the force of the wedge on the cart, and that exact same force needs to show up backwards on the cart. So we need to basically take this one and just turn it around 180 degrees like this. Oops. I'm going to try my best to make them line up with each other, because I want them to be exactly the same, but just backwards. So that should work. So that is your other force. And I'm just going to call this one N. I'll make it blue, though. I'm just going to call this one N. And there we go. We do need to figure out what these angles are, but I'm just going to leave it to you to prove that that angle right there is going to be theta. And I think that's it. Those are all of our forces. In addition to these, of course, we have our acceleration. It's not a force, but we want to draw it on our picture. The acceleration goes that way, which means we're going to make this direction the positive x direction, and we're going to make this direction the positive y direction. Again, because, just to keep repeating, the acceleration and the positive x direction need to be the same direction. That means that we only need to break up one force. That is this one right here, the normal force. So we're going to break that up into components, and there's going to be one that goes this way, and then one that goes straight down this way. And those will be n sine theta over here and n cosine theta over here. And again, this is the Newton's third law pair. The normal force is the force of the wedge on the cart, so this is the force of the cart on the wedge. those are a Newton's third law pair. Okay, so now the only other thing to do is to just start using Newton's laws on these right here. We're only actually going to need one of the two equations, so I'm going to write that one down. I'll probably write both of them down, but I'm just going to start off. Net force in the x direction is going to be equal to now big M times A because, well, this is the wedge and has a mass big M. The forces acting in that direction are F, which points to the right, and in sine theta, which points to the left. Those should be equal to big M times A. And now we actually have enough information to solve our problem because our goal is to find F, which we know. And we already have the acceleration from the previous part and the normal force from the previous part. So we really just need to plug them all together, right? So what we're going to get is F is equal to, plug in from the normal force from here, so that's mg over cos theta, little mg this time, times sine theta, plus, how are we doing on time? I think we're fine, plus ma, which is going to be m, and a was g tan theta. So combining everything together, sine over cosine is also tangent, so both of these terms have a g tan theta in them, which we can factor out, and all we need to do is just write m plus m, or the total mass of the system, multiplied by g times the tangent of theta. And that's our answer. There's a lab manual problem that's like this. It's not exactly the same, but it's similar. In the lab manual problem... Okay, I should stop for a second before I jump to more harder, difficult things. You all have any questions? So there's a problem in your lab manual that looks kind of like this. It's kind of a combination of this problem and the problem that we did with the pendulum that was hanging. God, this looks awful. But it's basically you've got a block that's got wheels on it, and then you have a cart that's sitting on top of it that has wheels, and then you have this cart is attached over a pulley to another like mass right here, and there's an angle theta that's made here between the vertical. And basically the question is, what is the force, basically? Something like that. I don't know. It's basically the exact same question, except like you just have three objects. Anyway.
Can you explain how you got theta for the normal force on the wedge?
On this one? Yeah, sure.
Yeah.
So this is theta. Would you agree with that? Alternate interior angles. Parallel lines. Cut by a transversal. Theta equal to theta.
Yeah.
Okay.
Gotcha.
So if that's theta, then this has to be 90 minus theta, because that's a right angle. And if that's 90 minus theta, then the blue angle has to be theta too, because this is a right angle. Does that answer your question?
Yeah, but can you explain again how you got the original theta on the under the green line?
This one?
Yeah.
Look at this picture over here on the left, okay? This angle is theta, right? Would you agree that that means that this upper angle is theta?
Yep.
Okay, it's the same thing over here.
Right there. Okay. Now I see it.
It's
Okay.
exactly the same.
Thank you.
No problem. Oh, it's not. Oh, there it goes. I was trying to undo some of this stuff. Just to leave the picture kind of clean. There we go. We have about almost 20 minutes, actually, to try to solve this last problem. I don't think we'll solve it, but we will at the very least get it set up to where we can solve it relatively quickly next time. This problem is... Whew. I've never done this... No, that's not true. I had to do this last spring. This is the kind of problem where I really wish I could show you a demo. Because we have these multi-pulley setups at the school, and I basically use it as a way to teach you how to solve these things, because I think it's pretty hard to get an intuition for how these multiple pulley systems work unless you can actually see it. So I should probably go find a video, or ask the lab tech to do a video for us, so you can see how this works. But anyway, let's start talking about it. So we have a 4-pulley system, and hanging from these pulleys is a mass M1 and a mass M2. We don't actually know what the values of these are, but we're gonna pick values later on, just to get an idea of what's going on here. So we don't even know which one's heavier. Like M1 could be heavier than M2. And another thing you don't know in advance is even if you knew that M2 was heavier than M1, do you really know if the system's actually going to go down and not the other way? Because the pulleys complicate things, right? So it says pick a direction for each acceleration and make sure they're consistent. So we're just going to pick a direction and just go with it. We want to find the ratio of the tension in this chord right here to the tension in this chord right here. And we want to find the acceleration of each block in terms of M1, M2, and G. And the way that this works, in case the picture's not clear, this first pulley is attached to the ceiling, and it's free to rotate. There's a cord you can see that connects M1 over that first pulley, under here, and then back up to here, right? What I want to do is I want to just look at that piece of the system and talk about it. Because I'm pretty sure I gave you a homework problem where you have a system just like that. So let's start off with just that piece and see if we can understand what's happening there. So I'm going to start off with a little circle to represent a pulley. That looks like circular enough to me. We're going to need another one of these, so we'll stop it. Copy paste, just copy paste, okay. So we're going to put two little pulleys like this, kind of right next to each other. And then we're going to wrap a string around both of them. We need a ceiling too, so they can be attached to something. So here's our ceiling up here. Leave me a little room in case I want to draw some other things. The pulley on the right is just directly connected to the ceiling, so we'll just put a little connection from there to there. I don't know why I wanted to make it red, actually. I want to make that black. So that's a connection directly to the ceiling right there. And then we have a rope that is kind of like wound around these, right? So let's draw some ropes in here. These ones I will make red. So I've got a rope that comes up this way, and then it connects to our pulley. And then that same rope continues around the pulley until it comes to the other pulley, which is right here. Let's move this over just a little bit. So it connects to the rope. And then, yep, so that rope goes down and it connects to that pulley. The rope continues back around here. And then it connects back up to the ceiling right here. And what we'll do is we're going to put, here, let me continue. So this rope goes up around here. And it continues down around this one. So this pulley here is basically just hanging freely. And attached to this pulley, we're going to put a mass. So I'm just going to put a mass right here. And we're going to say that it has a mass of, I don't know what, we're just going to call this one M2 or something. And then connected to this one over here, let me make this cord longer. We'll put another box right here, and we'll call that one M1. And we're just going to try to understand what happens with these double pulley systems and how they work exactly. So the first question I would ask you is, if the system is at equilibrium, so if the system is in equilibrium, just think for yourself, take a guess, because I want to kind of know what your intuition is. So if these two were perfectly balanced in the situation they are right here, okay? So nothing's moving. Which of these two masses do you think would be heavier? And you can write your answer in the chat. And again, I don't care if you're right or wrong, I just want you to take a guess. Which one do you think's heavier? And I appreciate it if like several of you took guesses. Just take a guess. Just like, if you don't know, just pick one. Just take a. If you don't know at all, just take a random guess. And don't assume that if you see a bunch of numbers, a bunch of people saying the same thing in chat, don't assume if they're right. Just take a guess. M4, yeah. Okay. So does anyone feel confident enough with their guess that they could try to explain why they think that one is heavier. So if you think it's M1, why do you think M1's heavier? You think it's M2, why do you think that's heavier? Anyone feel confident enough to... And you can cue your mic and say something if you want to. The weight of M2 is stopping the system from accelerating. Prevent. Yeah, M1 would naturally want to fall, but it's balanced out by M2 because it's longer. It hangs lower. Yeah, I made it lower just because I wanted to be able to draw inside of here, but I can see why. Yeah. Okay, so let's start thinking about this in terms of the forces. We'll just use Newton's laws, and we'll try to see if we can work it out with Newton's laws. Okay. So what are the forces that would be acting on M1? If I were to draw a free body diagram over here for M1, what would the forces be? Tension and weight, right? Okay, and they have to be equal to each other basically because it's at equilibrium, right? So equilibrium means net force equal to 0. So these two forces have to be the same, right? All right, so we know that T is equal to M1G now. That's the tension in the cable. Now, one thing about chords in physics is that if I have a chord and it goes all the way up here and then around here and up here, it turns out that the tension in the chord is the same everywhere. Okay? So if I tell you that the tension in the chord down here is T, right? That means the tension in the chord up here has to be T. Okay? In addition, that means that the tension in the chord here also has to be T. But that's going to get confusing. I need some room. That means that the tension everywhere in this cable is T, right? So if we were to look at this pulley right here, that means that the tension in the cable on this side is the tension T, and the tension in the cable on this side is also the tension T. Right? Right, so what does that mean on the other side over here? That means on the other side, the tension has to be 2T. Right? So if I was to draw the forces acting on M2 right here, what I would do is I'd say, okay, for M2 I've got its weight, which goes down this way, and pulling up on it is this tension 2T. And for this one, we would say 2T is equal to M2G, right? But T was equal to M1G. So that means that M2 has to be how much bigger than M1? Yeah, M2 is basically, we can plug numbers in. So then we would get 2 M1G is equal to M2G, which means that M2 is 2 times as big as M1, right? So for example, if M1 was 1 kilogram, M2 would be 2 kilograms. If M1 was 10 kilograms, this would be 20. If this was 37 kilograms, this would be whatever 2 times 37 is. M2 is twice as big as M1, right? So what you can think about in order to help you remember this is how many cables in our picture right here are supporting M1? How many total cables are supporting M1? There's just one, right? And how many cables are supporting M2? There's 2. And it's the same cable, right? So that means that M2 has to be twice as big because it needs 2 cables to support it compared to M1. And that's how these double pulley systems work, right? If you think about this, this is a nice simple machine here, this combination of these pulleys, because what this says is that a mass, let's put some numbers in here. Suppose this was 8 kilograms, okay? And say that this one over here then would have to be how much? 16 kilograms, right? So just due to the combination of these pulleys, you could support a 16 kilogram object with something that only has a mass of 8 kilograms, right? Does that make sense? You could support a 16 kilogram object with an object that is only 8 kilograms. Half as much, right? That means that take whatever the biggest weight that you can lift. Let's say that the biggest amount of weight that you can lift or the hardest that you can pull on a rope is 50 pounds, right? That's as hard as you can pull. And let's say that you have a load that's 100 pounds and you need to lift that load and put it into a truck or something like that, right? Well, you alone can't lift the 50 pounds. And if you don't have anyone nearby that can help you with it, maybe you could set up some kind of a pulley system that can help you to lift it by exerting your downward force of 50 pounds to lift something that's 100 pounds, right? And of course, this is just 2 pulleys. It turns out that if you add together multiple pulleys, every time you add in a pulley, you cut the load in half, okay? So what we're going to prove in the problem over here on the left, which we're going to do here in a second, is that the effect of each one of these pulleys is to cut the force down in half, okay? So what that means is that if M1 had a weight, let's say, of 1 pound, M2 could have a weight of 8 pounds. It'll be an 8-to-1 ratio. If M1 was 100 pounds, you could lift a weight of 800 pounds. That's kind of incredible to think about, right? That if you could just pull with a force of 100 pounds, you could lift something that's 800 pounds, right? Maybe a small car. I don't know if a small car would weigh 800 pounds, but probably, right? Cars tend to weigh about a ton. A ton is about is a ton 1,000 pounds or is it 2,000 pounds? I forget. I think it's a ton. 2,000 pounds? I don't remember. It's 2K? Yeah, okay. So if you wanted to lift something that was a ton, and you could only lift 50 pounds, just take that ratio, 2,000 divided by 50, which is what? 200 over 5, which would be 40, right? So if you just get 40 pulleys together, then you can easily lift a ton. So there you go. That's how these double pulley systems work. Does anyone have any questions?
Why is T going down on that one part of M1?
Up here?
Yeah.
Oh, just that's the tension that's acting on the upper pulley, basically. I mean, the tension's the same everywhere, but on the upper object it pulls down, on the bottom object it pulls up. Okay. Now there's a cost that you have to pay in this, okay? Because this is the other part of this problem that's kind of tricky. So if we take our arrangement here of all these pulleys, the double pulley system right here, if I pull M1 down by some distance, like let's say that I pull M1 down by a foot, right? How much is this pulley going to move up by? Does that make sense? So I take a system where I have this double pulley system going on, right? I've got my mass down here, M1. I've got my pulleys here, and I've got my pulley here, right? And then I've got my weight here that's M2. If I were to... Or wait, we need one more line, right? We need a thing connecting right there. There we go. That's a whole system. If I were to translate this down by, let's say, 2 feet. Let's say that I move M1 down by 2 feet, okay? How high is this going to move up? How high is the pulley on the left going to move up? 1 foot? It's a good guess. That is the right answer. That is the right answer. If you move the pulley on the right down by 2 feet, the pulley on the left is going to only move up by 1 foot, okay? So you never get anything for free in the world of, in the real world. And physics is no different. So just because I can lift a 16 kilogram object with a force of only 8 kilograms, the distance that I need to move the smaller object is twice as far as the distance that I need to move the upper object, basically. Does that make sense? So while I can pull down on the right object and make the other object move up, it's only going to move half as far. Can anyone tell me why the one on the left is only going to move half as far? God, I wish that we could I could do a little demo and show this to you and have you all come up and play with it, because you would see instantly why this happens. It's really obvious if you can see it, but picturing it in your mind is, I think, very hard. Any ideas why the one on the left would only move up 1 foot while the one on the bottom moves down 2 feet? You had the right intuition, so there's something there, Andrew, that you do understand something about what's going on here. So if you look at the rope, this is the key thing. You got to look at the rope. If, for example, I think I can draw on this picture right here. Think about, this is the initial level, right, of this pulley, right? It starts off right there. If I were to take this cord and I were to move M1 down, it's because there's 2 pulleys. That's exactly right, Chris. If I were to move M1 downwards, you all agree that this pulley has to go up to compensate for that, right? And that happens because if I make the one on the right go down, I have to pull cord. I have to pull cable from somewhere, right? I need to increase the length of the cable between here and here, right? So let's say right now it's like 6 feet. If I pull it down by 2 feet, then the length of the cable between here and here would be 8 feet, right? So that cable has to come from somewhere. Where's it going to come from? Well, if you think about it, the distance between this point up around this semicircle right here to this point, that distance is fixed. It can't come from there. That distance has to stay the same. In addition, the distance between these 2 points on the bottom semicircle over here, it can't come from there. That can't change either. So, when I pull the cord on the right side, the only place where the rope can come from is basically between these 2 line segments here. This line segment here, and this line segment here. Those are the only 2 places that I can actually pull the rope from if I want to move this one downwards. Does that make sense? Between the ceiling and here, and this point here and here. And I need to pull equal amounts from both sides. So what happens is that this is going to move up half as far as the one on the right moves down, because I'm feeding cable onto the right, and it has to come from 2 places, left side and right side, so it needs to come equally from both. And that's the reason why that this happens. We're going to have to finish solving this tomorrow, but I've taught you all the things you need to do to solve the homework problems on this, because your homework problem that's related to this is not nearly as difficult. I think it's just, I literally think it's this setup right here, and you just need to find the ratio of the accelerations and the ratio of the weights. You now know how to do that. I will say that because the distance that the one on the right moves is twice as far as the distance the one on the left, this is going to have an acceleration that if we called this one A, then this one's going to move upwards with an acceleration of A over 2, because the distance and the acceleration are related to each other. And yeah, so we'll try to solve this problem next time. I think next class is going to have to be a little bit longer than normal. I think we'll need like at least an hour and a half or 2 hours to solve all the problems that I want to solve. But